All right, so we're going to draw the shear force and bending moment diagram for this frame. So a little strategy. We'll find the reactions at A and C first. Then we'll separate the structure here at B and find the internal forces there, two forces in a moment. And then with that information, we should be able to draw the shear force and bending moment diagram for BC and AB. So I'm going to start by finding my reactions. At A, I have a pin, so I'll assume a force AY and a force AX. And then over here at C, I'll assume a reaction. I'll call it CY. You guys will have to help me with some calculations probably, but we know the concentrated equivalent force of that distributed is 4 kips per foot times 10 feet, so that's 40 kips. And half the distance, that would be 5 feet. I think that's all we need to find the reactions. So I'll sum moments about A, make sure they're in equilibrium. So about A, these two forces along the side section here, AB, they create positive or negative moment? Negative. So the first one is 10 kips, and its moment arm is 4 feet. The second one is 15 kips, moment arm of 8 feet. Then I've got the concentrated equivalent force. What's that creating? Positive or negative moment? Negative. That's 40 kips, and its moment arm is 5. And then I have CY, which is positive moment, and has a moment arm of 10. So we should be able to solve for CY. What is that? 120 and 40 is 160. 336?
36.
Yeah.
So 36, and it's positive. Cool. So now we can sum forces in the y direction. So we have AY acting up, CY acting up, and then minus 40 kips acting down. So that tells us that AY is 4 kips. And then we'll check equilibrium in the x direction by summing forces in the x direction. We'll say to the right is positive. So I'll start with AX, then plus 10, plus 15. So that says that AX is minus 25. Okay? Any questions about that? That's a pretty typical start. Now let's break it apart. And I'm going to look at, let's look at section AB. So if I were to draw a free body diagram of that section, I'll start by putting my reaction forces on it correctly. So AY we saw as 4 kips, so I'll have 4 kips acting up. AX was negative 25, so it's to the left. There's my reactions. And what else do I have? About mid-height, I have the 10 kip force. Up here at the top, I have the 15 kip force, 4 feet, 4 feet. And now I'm cracking the thing open at B, and I'm going to assume a force BX, BY, and moment. So before we can even start drawing the shear force and bending moment diagrams, we have to really work hard and do a lot of statics. So now I have to solve for these three unknowns. Let's do that. So I'll sum moments at B. And why would I do that? Well, two of my unknowns pass through B, so all I'll have unknown will be the moment at B. Now, I'm using right-hand rule, so this moment is what? Positive or negative? Positive. Now, the 15 kip force, you can see, really passes through B, has no moment arm. But the 10 kip and the 25 kip do create moment. What about the 4 kip here at the bottom? No, it passes through B also. This is going to be a positive moment, so I'll say 10 kips times a moment arm of 4. And then the 25 is going to be negative moment, and it'll have a moment arm of 8. So from this, I should be able to find my moment at B. It looks like it's going to be positive. That's 200 minus 40 is 160.
Yeah.
And that should be kip B. Okay? Now what? Let's sum forces. So if I sum forces in the y direction, make sure we have equilibrium. What do I have? I've got By acting up and 4 kips acting up. So it looks like By is negative 4 kips. That wasn't so hard. And then sum forces in the x direction. Make sure they're in equilibrium. What do I have in the x direction? Well, I've got 15 plus 10 minus 25 plus Bx. So I got Bx is positive plus 15 kips plus 10 kips minus 25 kips. Looks like Bx is 0. Okay? So that's all the information we need to be able to draw the shear force and bending moment diagram. So let's do that. I had another sheet here somewhere. I thought I did. Oh, it's underneath. There it goes. So which one do you want to start with? A, B, or B, C?
Which is easier? Whichever one's easier.
Whichever one's easier? Probably A, B would be easier. So just to help you orient yourself, I can rotate it up here. So I'm going to draw A, B in this configuration. So my shear at A is going to be what? AX. And then I'll have these forces, and then BX in the moment. So I'll go back and rotate it back, and I'll draw that here. So now I'm going to draw a beam, and let's see. We found AX was 25, right? And it's in this direction. Now, a force in this direction on this beam, is that positive or negative shear? Positive. And then we found Bx to be 0. And then about middle of the way, we had our 10 kip force. And at the end, we had our 15 kip force. And this was at 4 feet, 4 feet. And then at the end, we had a moment, which we solved for. It was in this direction, and it had a value of 160 kip feet. So I'll go ahead and draw my template. There's the sides. This midpoint is going to be important for us. Slide that up a little bit. Let's start with the shear diagram. So So I'll denote my positive x-axis, my positive shear axis. All my units will be in kips. So what's the initial shear at A? It's positive 25, right? I can give myself enough room. Sorry about that. Now remember, the change in shear is the area under the load diagram. So what's the area under the load diagram over the first 4 feet? 0. So there's no change. So my shear remains 25. Now the slope of the shear diagram is equal to the load. And what's the load everywhere? Come on, you can play along. 0. That means 0 slope. 0 slope produces a horizontal line. So over the first 4 feet, we have a constant shear of 25. Now, as we go from the left side of this 10 kip force to the right side, what happens to the shear? It changes how much? 10 kips, positive or negative? Negative. So 25 minus 10 brings us to 15. And then the change in shear over the x 4 feet is the area under the load curve, and that is 0. So it stays at 15. You'll also notice that the slope is equal to the load. The load is 0, so the slope is 0, horizontal line. So this kind of stair-stepped shear diagram. Okay? Now what? On to moment. So here's the x-axis. There's my positive moment. Units of kip feet. What's the moment at A? 0. What's the bending moment at B? Positive or negative? The way I've drawn it here, positive. So I know where I'm starting. I know where I have to end. Let's see what it looks like in between. So I know that the change in moment is the area under the shear diagram. So over the first 4 feet, what's the area under the shear diagram? It's a rectangle, so it'll be base times height. 4 times 25 is 100. That's positive. So that means I go up to 100. What's the slope of my moment diagram? Well, by definition, the slope at any point is the shear. And the shear is constant, positive, and equal to 25. So I get this line. And if I ask you what the slope was, it would be 25 to 1. Now the change in moment from 4 to 8 feet is the area of the shear diagram. What's this area of the shear diagram? 4 base, 15 height, 60. 100 plus 60 is 160, so it matches. The slope of the moment diagram is equal to the shear. What's the shear everywhere there? It's constant and positive 15. This is not the scale, but you get the idea that now this is 15 to 1. And there's my moment diagram. So what's the maximum moment in this beam? 160, and it occurs at B. So now let's do the other portion, which would be the section from B to C. So I'll come up here now. Let's look at section BC. I guess I should have named this one over here. This is AB. So I'm going to redraw the structure. So I've got this distributed load on it of 4 kips per foot. Okay, what's happening at C? If you remember our calculation, we found that CY was up and equal to 36 kips. Now, what's going to happen here? Let me slide this back just for a second. Remember when we solved this problem, we found that BY was negative 4. Well, that means on section BC, it's equal and opposite. So it would be down, but it's negative, so it's actually up. That's going to be a value that's up of 4 kips. The moment at B equal and opposite is in this direction, and it's equal to 160. That should be everything that's on there. That make sense? Yes? No?
Yes.
Okay, cool. So let's proceed. So I'll draw my template. Right now, that's all I really know what to do, just have a distributed load. I think something's going to happen here on the shear diagram. We'll need another point here in a second. So here's my shear diagram in kips. Okay, so what's the shear at the beginning edge here? 4. Positive or negative? Well, I were to give it away. And at the end, it's going to be, yeah, I'm not going to draw, this is not going to be to scale for sure. Now, the change in shear should be